here we are. Um, this is one of two lectures that I'm posting to replace the fact that we won't be in class Thursday morning because I'm at a lecture. In fact, I just realized as I hit go on this, I still had my nerd tag on from the conference, so I'll go ahead and remove that from the equation. The other thing that's a little different, and I'm not real happy about it, but I've had this problem before. The way I typically do this with my iPad requires that I be on be in the same local network or something like that, and it's not working at this hotel. I don't know if they somehow the way it's configured, it won't allow me to handwrite notes on my iPad and make them appear on the screen. So what I'm having to do instead is I took the time to just PowerPoint up what I wanted to say. So it's okay, but I know that in the past some students have not really cared too much for the PowerPoint notes. I think they, for some reason, like to see it written out by hand. What I can do when I get back this weekend to Bowling Green, I can, if you prefer, let me know. Just send me an email, let me know. But I can go through and retape these lectures and do them by hand. And I don't know. I don't fully understand it, but I know that some students get more out of the lectures if they see me actually write them by hand, and that's fine. I do tend to write a little bit more when I'm doing it by hand because when I do it with PowerPoint, I know that I have limited space lots of times, and so I have to crowd stuff in. So if you do want me to go this weekend, if you want me to go back and retape these with my iPad and doing it with a stylus and writing stuff by hand, I was fully prepared to do that here. Just the way the network here at the hotel is set up, it just won't let me do it. So, but anyway, let's look at what I want to talk to you about today. It's in PowerPoint, but hang with me on that. Now, there's actually two parts of this next bit of material. We're going to be talking about mathematical induction and as a way of proving things. It is a very powerful tool in our toolbox for proving things. There's certain cases where we cannot use it, but there's also very powerful cases where we can, and it makes it look like we can do marvelous, wonderful things, and really we can, but it's really going to bump us up a notch. It's not complicated, but I do want you to understand why it works. And then what we'll do with the second lecture, the part 2 lecture, is talk about how you can broaden and what's the word I'm searching for here? Use it in more powerful ways to prove more powerful things. So what we're going to look at today is the basic idea of mathematical induction, and then we'll expand upon that in the part 2 lecture, which I probably will tape in the morning. If you actually, I'll send a notice that I've posted this. The other one I'll probably do early in the morning because I've got to run off to a dinner here in just a little bit. But let's get going on the idea. We're going to move into 2.2 in your book, which has us proving statements using mathematical induction. And sometimes they'll say do a direct proof and then do an induction proof. But so I'll show you both, but I really want to show you the power of this tool of mathematical induction. And before I can do that, I need to explain to you what it is. The idea is that we are trying to prove a statement, P of n, for all integer n bigger than a. Now, it's important to point out that if we're trying to prove something for all reals, for example, this is not a tool we can use. We have to be able to list things out. We have a starting point, be it 0 or 1 or whatever it is, and we start there, and then we look at one integer bigger and one integer bigger. So we do have to have that countability of the set. And we could even, you could even, if you really wanted to, we won't do this, but you could even expand this to some kind of index set. As long as it's countable, it doesn't have to even be integers, but as long as it's a countable set, you could do it. That's fine. We're going to deal with things on integers where that statement depends upon the integer n. And then our proof technique will be And I've already shown you one of these. I think we did, if we sum up things from 1 to n, then you get that formula, and I'll go through that again in just a second. But the idea with induction is, wherever that starting point is, you prove that the statement is true for that starting point. Okay? And then you prove that if I assume it's true at any integer above the starting point, then it has to be true for the next integer. Okay, so whatever k I pick, and we want to be very general in that, we can't pick it. It only works here. No, for anything I pick bigger than my starting point, if it works there, show that if it works here, then it works there. Okay? And so what happens is, here's your starting point, the proposition for A, and here's the statement for A plus 1, A plus 2, and A plus 3, and on and on and on. Okay, we prove the first one. And then out here, if we say, okay, it's true for this one, if we assume that, then we get the next one. Well, what that enables me to do, because this is a general k greater than A, greater than or equal to A, I can go back to the statement for A, and that proves then A plus 1. And then, since A plus 1 is true, A plus 2 is true, and so on, and so on, and so on. And so that actually proves it then, that statement, for all integers A and above. Okay? It's a very powerful tool when we have that situation, and we can prove some just ridiculously messy formulas and even some situations that you think, that's how you supposed to do that. Induction can help us do that. So let me give you some examples. I want to show you a couple of examples. One is the one that I think I did this on the board in class. It's attributed really to Carl Friedrich Gauss. Not that he proved the theorem and wrote it up, but he was a 10-year-old kid, and he, the teacher gave him gave the whole class, I think, some busy work saying add up the numbers 1 to 100, and he just, he's like, oh, that's 5,050, and this is supposed to be probably the technique that he used to do that. So the direct proof of this is what I think I showed you on the board. You list things out 1 to n, and then you list them out in reverse order. So every time you add these things up, you're getting n plus 1, and you get n of those. So n times n plus 1, and to do this, you've actually doubled the sum, so divide by 2, and you got it. And that's what I did up on the board, I think, in class. And then your statement, therefore, it's true. Well, let's look at it using mathematical induction, okay? So with an inductive proof, first thing I would do, this is going to hold for n equal to 1 if that's where we're starting at. So as long as n is 1 or bigger, then this formula should hold. So what you do is, okay, first things first, let's get that starting point. Let's prove the statement actually holds for n equal to 1. Okay? So really, when you just do that once, you're just putting a 1 in there. J is 1, and that's it. So you get 1. The formula, if you put a 1 in here, you get 1 times 1 plus 1, which is 2. So those 2's cancel, and you get a 1. So the formula actually holds for n equal 1. Okay? Now, and you got to be, this is where it gets a little, I keep referring you back to the way we describe this. He's like, well, how can you assume it works for k? Well, we can assume whatever we want, okay? The point is that once we have that assumption that we can get the next one, then we can go back to 1, the case where n is 1, and that proves n is 2, and that proves the case n is 3, and so on. Okay, so this next step is not the entire proof. This is part of the induction proof where we say, okay, assume that it does hold. Okay, now this is for k, all right? And this is where it gets a little funny because you think, well, you can't assume that. In fact, I've been harping on this. You can't assume it's true. I'm not assuming it's true. I'm assuming it's true for some k. Okay? Not all integers 1. That's what I got to prove. 1 and bigger, that's what I got to prove. But let's assume it holds for one k out there somewhere, or for some k in general. Okay? I'm sorry, I didn't mean to say okay. Yeah. And then consider what happens when we look at the next one. Okay, where instead of going to k, we go to k plus 1. All right, now sums are actually quite easy to extend one more thing, right? If I look at this sum, I can actually take it out to k and then add the next term where j is k plus 1. Okay? So this part, the sum where it goes up to k, my assumption is I have a formula for that. So I can then substitute in that formula. And then I can get a common, well, before I get a common denominator, I've got a common factor that I could factor out, the k plus 1. That would leave me with k over 2 plus 1, right? Then get the common denominator. So I have k plus 1 times k plus 2 over 2. But if you'll notice, that is exactly this formula with k replaced with k plus 1. K plus 1 is k plus 2. And so this is where we close up the proof and we say, all right then, this statement then holds for k plus 1. Therefore, by induction, the statement holds for all integer n 1 and greater. Okay? I'm sure down the line you've probably seen a teacher go through an induction proof. The difference is now I'm going to have you doing induction proofs. Let me show you another example so you've got a little bit more to go on. And there's a few examples in the book too that you can take a look at. Let's look at another formula. In fact, I'll look at another formula that's a sum. The sum of r to the j power as j goes from 0 to n. What I'd like to show is that it is this formula, this 1 minus r to the n plus 1, so whatever this is, raise it up a power, divided by 1 minus r. For non-zero r and for non-1 r. The non-zero comes from the fact that 0 to the 0 power really doesn't make any sense, so I don't want to include that in here. And the 1 comes from the fact that putting a 1 in this formula gives me a 0 in the denominator, which I don't want to do. It wouldn't be that hard anyway just to get that formula right. If r is 1 and I'm raising it to different powers, it's always 1, so whatever n is, the answer is n, right? That's not hard, so we don't need a formula for that. And I want to show that this holds for any integer n, 0 or bigger. Okay? So remember what happens with an induction proof. First you start at the starting point, you prove that the formula holds at the starting point. Then you assume, okay, here's some k. We'll assume it holds a k, show that you could do it for k plus 1. And then you can go back to this one and get them all. Okay? So let's start with the starting point, 0. Okay. Oh, you know what? I forgot to even put this in. I'm losing my mind. You can prove this directly using almost Gauss's trick. I just want to show you this real quick. I won't charge you tuition for this part. But just to show you how you would normally, one way you could knock this out quite simply. Doing the same thing that Gauss, the Gauss's trick thing, except multiply. Now we're looking at changing the exponent, not the number, right? And so multiply by 1r and then subtract. And what happens is instead of 1, you get r. Instead of r, you get r squared. So you notice all these things are bumped up 1 power because we multiplied by an r. And then you're subtracting. So because these things do line up, you keep the 1 here, you subtract, and you get rid of all these other things, and then you subtract r to the n plus 1. And then solve for s. So you can factor out an s, you're left with a 1 plus r equals this, divide by the junk, and there you go. Okay, that is the direct proof of this. Okay, now, let me go back. Induction, we start with n equals 0, because that's our starting point. And we say, okay, if I plug in a 0 here, I just have the one term, r to the 0, and that's 1. Okay? And if I look at my formula, I've got 1 minus r to the 1, which is just r, over 1 minus r. 1 minus r over 1 minus r is just 1. Okay? As long as that's not 0 over 0, right? Okay. So we've got the starting point. Now let's go out here and assume it holds for some k. Okay. And again, I want to stress to you, this is not assuming the proof. You know, we have this thing that I kept kind of beating into your brain. You can't prove a theorem by assuming it's true, right? Well, it kind of looks like we're doing that, but we're not. We're just assuming that it holds for a general k. Just pick a k, and we'll say it holds. Okay. If it holds, then the next one holds. That's what we're going to prove. But that hasn't actually proven it true for either one of them yet. The proving it true for either one of them comes when I go back to the first one and say, okay, right then, if it works for 0, then it works for 1. And if it works for 1, it works for 2, and so on and so on. Okay? So we're not assuming the proof is true to prove that it's true. I want to stress that very carefully. We are saying for a general k, let's assume that it holds. Okay? And now look at that sum when we go up to k plus 1. Another sum proof. Okay? So again, with induction, write it up to k, and then take the k plus 1 term and separate it out. Okay? Now this thing, we have a formula. It's this. And then I've got the r to the k plus 1. All right, it's a fraction. I'd like to get it out to this where I've replaced this k with k plus 1. So common denominator makes perfect sense, right? Get 1 minus r in the denominator here and in the top there. And then multiply things out. I've got 1 minus r to the k plus 1, and then I've got plus r to the k plus 1, and then minus r to the k plus 2. Right here. And you'll notice that these are the same thing with different signs, so they're gone. And this formula, if you will, is this formula with k replaced with k plus 1. So we've proven that inductive step holds. Okay, if I assume it works for k, it's going to hold for k plus 1. Therefore, when I go back and do them all, I've actually shown it works for all of those integer n that are greater than or equal to 0. Okay? Two examples of proofs done by induction. If that was a little fast, the other thing with PowerPoints I've noticed, I tend to go pretty quick sometimes. You know, you've got control over that business. You can pause, you can stop, and take a look at it. If you have questions, email me. Perhaps I can help you. What I will do in the morning is I will post the part 2 of this lecture and look at ways we can adapt the induction idea to where it looks like we're making stronger assumptions, but they're still okay. And it actually helps us solve more complicated problems. Okay? Your homework out of this little part will be out of 2.2 in your book, problems 2 through 4 and 6 through 11. And then we've got a few more things to tackle on Tuesday, and then we'll move into these problems. Okay. All right. That's it for me on this part. I'll talk to you again in the morning, and we'll do an extension of this called strong mathematical induction. All right. See you.